Our research motivation stems primarily from a four-dimensional heuristic exploration. First is the deep practice of environment construction, where we strive to understand the architecture of a standard reinforcement learning training pipeline from scratch. Second is the deconstruction of algorithmic logic, deepening our grasp of convergence mechanisms through low-level code implementation. Additionally, we focus heavily on the differentiated analysis of algorithmic characteristics. Within a unified simulation environment, we conduct horizontal comparisons of on-policy versus off-policy, and value-based versus policy-based algorithms. Specifically, we examine their performance variance when handling high-dimensional visual inputs to analyze the adapted logic between intrinsic algorithm traits and specific dynamic environments. Given the extensive research already available in the field of basic algorithms, we have strategically focused on this report on the evolution and optimization of learning algorithms. Our goal is to explore the performance ceilings of reinforcement learning and complex continuous control tasks through reproduction and iterative refinement. Our ultimate goal is to achieve the best possible score on the car racing task. Our roadmap is fourfold: establishing a 400-plus reward baseline, conducting qualitative theoretical verification, pursuing SOTA performance through engineering optimizations, and deepening our understanding of RL mechanisms through rigorous trial and error. We utilize the car racing V2 or V3, which is a standard benchmark for continuous control within the Gymnasium ecosystem. Its primary challenge lies in fine-grained control via visual inputs, requiring complex coordination of steering, throttle, and braking. Literature highlights significant issues with sparse rewards and long sequence dependencies. Currently, SOTA methods are predominantly based on PPO algorithms combined with geometric reward shaping. We trace the evolution of algorithms. Starting from the original reinforce in 1992, policy gradient methods have evolved from high-variance Monte Carlo estimations to sophisticated actor-critic architectures. Our work leans heavily on the PPO algorithm proposed in 2017, which balances the sample efficiency and training stability through clipping and GAE. We also analyzed DDPG. While it offers theoretical advantages for continuous spaces, it remains prone to instability when handling high-dimensional visual inputs. We examine value-based methods. When DQN and double DQN successfully addressed Q-value overestimation, they face inherent limitations in continuous control tasks. Discretizing the action space leads to a loss of precision, resulting in jagged trajectories on the track. Similarly, while SARSA is robust as an on-policy method, it is often susceptible to becoming trapped in local optima during complex tasks. Turning to section 1.3.4, we dive into reward shaping and execution layer optimization. Building on NG theories, we develop refined mechanisms such as effective progress rewards and centerline potential fields. Crucially, we drew from industrial PID control theory to propose a low-frequency decision plus high-frequency execution dual-layer architecture. This utilizes a PID controller as a post-processing tool to eliminate high-frequency neural network output jitter without requiring model retraining. Finally, please refer to section 1.3.5. We adopted a shared backbone design to ensure visual consistency between the actor and critic decision logic. Regarding training techniques, we applied orthogonal initialization and gradient clipping to prevent explosions, alongside task-specific gas bias tricks, which significantly enhanced exploration efficiency in the early stages of training. Our overall technical roadmap is divided into three key stages. First, algorithm implementation and baseline achievement to verify fundamental feasibility. Second, qualitative analysis and theoretical verification to predict performance based on action space and stability. And finally, performance optimization and high-score challenges through engineering refinements. In Phase 1, we reproduced 6 basic algorithms ranging from reinforcement to PPO and unified the pre-processing pipeline. In Phase 2, we predicted performance by analyzing code features and verified any discrepancies between those predictions and actual results. During the Solta challenge in Phase 3, we selected PPO as the optimal algorithm, implementing reward-shaping mechanisms and a PID controller for action smoothing, while also increasing the environment frame rate to 120 Hz and optimizing the network strategy. During our initial environment selection, we attempt to transform Stardew Valley into a reinforcement learning task centered on tree chopping. Our technical approach involved using SMAPI for data interception and connecting the C+ game client to Python GPU training client via the socket protocol. However, we encounter 3 fatal issues. A critical training bottleneck due to the inability to accelerate the game's massive engine. Data communication flaws where high-frequency sampling led to significant data loss and discontinuous states, and a reward design dilemma between sparse rewards and reward hacking that consistently prevented convergence. This failure provided a crucial insight. Training speed is the ultimate bottleneck in RL experiments, and a viable environment must possess stable, low-latency data interaction capabilities. After reflecting on the limitations and failures of our earlier experiments, we ultimately selected the Gymnasium car racing V3 environment as the experimental platform for this work. Car racing V3 is C-compiled, lightweight, and widely recognized as a standard benchmark in reinforced learning, particularly for continuous control tasks based on visual inputs. Compared with our previous attempt using the Stardew Valley environment, Car Racing V3 provides substantially higher computational efficiency, stable and continuous state transitions, and a native support for both discrete and continuous action spaces, which makes it well-suited for fair and systematic comparisons across different algorithm families. In contrast, the Stardew Valley environment suffered from several fundamental limitations, including extremely slow execution speed due to the inability to accelerate the game engine, unreliable socket-based communication that frequently caused packet loss and state discontinuities, and a high complex reward design that oscillated between sparse rewards and reward hacking. These issues collectively resulted in extremely low training efficiency, rendering large-scale reinforcement learning experiments impractical. Car Racing V3 avoids these problems by relying on direct memory access, a clean and intuitive reward structure, and stable continuous dynamics. And it generalizes well as a benchmark environment rather than being constrained to a single handcrafted task. We next define the environment specifications and preprocessing pipeline, beginning with the design of state space. For image preprocessing, we first convert RGB observations into grayscale, since color information is largely redundant for distinguishing the track from the grass, and grayscale images are sufficient for perception while significantly reducing input dimensionality. We then resize and crop the original observations, as empirical inspection reveals the status bar at the bottom of the screen introduces irrelevant noise for decision-making. Cropping the image to 84 × 84 both removes the noise and reduces computational cost. To compensate for the lack of temporal information in single-frame observations, we apply frame stacking and use the classic 4-frame stack, enabling the agent to amplify infor-motion-related cues, such as velocity and acceleration from visual changes. It should be noted that, due to time constraints, the final Solta version of our algorithm adopts a 96 × 96 input resolution instead of the unified 84 × 84 setting. Ideally, all algorithms would share the same 84 × 84 preprocessing scheme for strict consistency, and this deviation should be regarded as a practical compromise rather than a conceptual design choice. Consequently, the final state space is defined as 4 stacked grayscale frames of size 84 times 84 for most algorithms, and 4 stacked grayscale frames of size 96 times 96 for the final PPO-based Startup model. In addition, the action space is designed according to the characteristics of different algorithm classes. For policy gradient methods such as A2C, PPO, and DDPG, we adopt a continuous action space with 3 dimensions, steering in the range from -1 to 1, gas in the range from 0 to 1, and brake in the range from 0 to 1, which enables fine-grained and physically realistic control. For value-based methods such as DQ and family and SARSA, we instead use a discrete action space consisting of 5 predefined actions, namely no action, turn left, turn right, accelerate, and brake, which aligns naturally with Q-value maximization and discrete action selection. Before formally reproducing and comparing different algorithms, we conducted 2 essential validation steps as a sanity check. First, we performed quick experiment using stable baseline 3 to verify that the environment itself was free of implementation bugs and that a standard agent could successfully learn to control the vehicle. Second, we implemented a human play.py script and manually interacted with the environment. This process allowed us to develop an intuitive understanding of the task difficulty and driving dynamics, which served as a concrete reference point for evaluating the behavior and performance of trained agents in subsequent experiments. One of the most important design choices in our system was the differentiated allocation of action spaces based on the fundamental principles of each algorithm, with the goal of allowing every method to operate in a setting that best matches its intrinsic strengths. For value-based methods such as DQ and family and SARSA, we adopted a discrete action space. These algorithms rely on explicitly computing the maximum action value, namely evaluating max over actions of QSA. When the action space is discrete, this operation becomes highly efficient, since the agent only needs to enumerate a small and fixed set of actions, including no action, turning left, turning right, accelerating, and braking. This design is not only computationally efficient, but also naturally aligned with the output structure of Q tables and Q networks. In contrast, for policy gradient methods such as A2C, PPO, and DDPG, we employed a continuous action space. These algorithms directly output the parameters of an action distribution, typically the mean and variance of Gaussian distribution, which makes them inherently suitable for continuous value control. Continuous action spaces allow the fine-grained behaviors such as steering while accelerating simultaneously, and therefore provide a significantly higher theoretical performance ceiling for racing tasks that involve continuous vehicle dynamics. Training efficiency was a major design concern in this work, largely motivated by the severe performance bottlenecks encountered in our earlier Stardew Valley project, where the environment could not be accelerated and large-scale reinforcement learning experiments become impractical. To address this limitation, we introduced Gymnasium's vectorized environment mechanism, enabling multiple environments to run in parallel during the data collection. Under this setting, the model no longer processes observations from a single environment, but instead receives batch observation from n parallel environments. For example, in environments simultaneously producing 96 times 96 visual inputs. This design not only allows better utilization of GPU parallelism, but also substantially increases sample diversity. In practice, these 2 effects jointly lead to significant improvement in frames per second and overall training throughput, making long-horizon visual reinforcement learning feasible within reasonable and computational budgets. We also place strong emphasis on how temporal information is represented in the state space. In the Stardew Valley project, the use of socket-based communication made it impossible to reliably record every frame state action pair, causing substantial loss for temporal information during training. This experiment led us to reconsider whether using single-frame images as states inherently discards crucial time-dependent information, such as velocity and acceleration. For a racing task, a single image alone cannot indicate whether the vehicle is moving fast or slow. Yet this information is essential for correct control decisions. To address this issue, we stacked multiple consecutive frames together as the inputs to the network. After reviewing prior literature and standard reinforcement learning practices, we confirmed that this approach corresponds to the classic 4-frame stacking, or frame stack technique. By stacking consecutive grayscale frames along the channel dimension, the network can implicitly infer motion dynamics from visual challenges, without requiring explicit speed or acceleration signals. To further reduce network complexity and accelerate convergence, we applied 2 standard yet effective image preprocessing techniques, namely grayscale conversion and spatial cropping. First, RGB observations were converted to grayscale, since color information is largely redundant for distinguishing the tracks from the grass in the car racing environment. Grayscale images preserve the essential structural cues required for perception, while significantly reducing the input dimensionally, thereby lowering computational cost. Second, we resized and cropped the original observations based on the empirical inspections of the rendered frames. The status bar located at the bottom of the game screen does not provide useful information for control decisions, and instead introduces visual noise. Cropping the image to 84x84 removes this irrelevant region and further reduces computational overhead, resulting in a more compact and task-relevant state representation. To improve training efficiency without sacrificing numerical accuracy, we fully adopted mixed precision training using torch.cuda.amp. By leveraging FP16 half-precision computation where appropriate, this approach significantly increases training throughput and frames per second. While maintaining stable optimization behavior and final performance, in practice, mixed precision training provided a substantial speedup and became an essential component of our overall training acceleration strategy. During policy network initialization, we manually set a positive bias for the output neuron controlling the throttle, specifically assigning the bias value of 0.5. This heuristic intervention, referred to as gas bias initialization, was introduced to address a critical failure mode observed in the early stages of training. Without this adjustment, the agent frequently remained stationary or spun in place near the starting position, even when the policy network appeared to output reasonable actions. As a result, exploration efficiency was extremely low, and a large number of collected samples corresponded to invalid or uninformative states. This behavior can be explained by several interacting factors. First, standard neural network initialization schemes such as Xavier or heat initialization produce outputs that fluctuate around 0, causing the initial throttle signal to be close to 0 on average. Second, the car racing physics engine requires the vehicle to overcome a non-negligible static friction threshold before any movement occurs. If the throttle value remains below this threshold, typically around 0.1 to 0.2, the car does not move at all. Third, when the vehicle is stationary, the reward signal is either 0 or negative due to time penalties, preventing meaningful gradient updates and trapping the agent in a stationary no reward, no update deadlock. Consequently, exploration becomes confined to a narrow region of state space corresponding to low speed or stationary behavior. We considered several alternative solutions, including directly rewarding throttle usage or increasing exploration noise. However, directly rewarding throttle input risks reward hacking, where the agent learns to press the throttle without learning to drive, while increasing exploration noise degrades training stability without fundamentally resolving the underlying issue. Gas bias initialization emerged as the most effective solution. By setting the throttle bias to a positive value at initialization, the agent is encouraged to press the throttles early in training, allowing it to overcome static friction, generate meaningful displacement, and collect informative driving samples. Importantly, this intervention does not alter the learning objective or constrain later behavior, as the agent remains free to learn when to reduce or release the throttle. Empirically, this technique significantly improved early exploration efficiency and contributed noticeably to the final sort of performance. In terms of network optimization, we consistently employ the AtomW optimizer together with gradient clipping to maintain training stability. However, our attempt to introduce dropout revealed a counterintuitive and ultimately negative effect. Motivated by standard practices in supervised learning, we initially added dropout with a rate of 0.1 to the fully connected layers to mitigate potential overfitting. Contrary to expectations, this modification led to severe training instability. The reward curves exhibited large oscillations and failed to converge reliability, and the final performance was significantly worse than that of the models trained without dropout, even after extended training. A closer analysis suggests several reasons for this failure. Reinforcement learning environments rely on Markov property, where the current state is assumed to contain all information necessary for optimal decision-making. Randomly dropping neurons during training effectively injects strong noise into the state representation, disrupting the information flow and violating this assumption. Given that reinforcement learning already suffers from sparse rewards and high variance, the additional stochastically introduced by dropout further amplifies instability. Moreover, the training objectives of supervised learning and reinforcement learning differ fundamentally. While supervised learning prioritized generalization to unseen data, reinforcement learning in this context prioritized deterministic policy convergence and ultimate performance. Introducing dropout before policy convergence makes it difficult for the value network to accurately estimate state values, dramatically increasing the variance of advantage estimates and leading to unstable updates. The inherent instability of reinforcement learning training is therefore exacerbated rather than alleviated by dropout. Based on these observations, we removed all dropout layers from network architecture. This decision was consistently validated in subsequent experiments and resulted in more stable training and better final performance. This outcome highlights the importance of not blindly transferring techniques from supervised learning to reinforcement learning without careful validation. We start from the standard reinforcement learning formulation, which is the markup decision process, or MDP. An MDP is defined by 5 components: the state space, action space, transition dynamics, reward function, and the discount factor. Within this framework, the main objective of reinforcement learning is to learn a policy that maximizes the expected long-term return. 2 central concepts in this framework are the value function and the action value function. The state value function describes how good it is to be in a particular state under a given policy, while the action value function measures how good it is to take a specific action in a specific state. The Bellman equations describe how these quantities can be recursively computed, and they form the theoretical foundation for most reinforcement learning algorithms. Based on this framework, we can broadly divide algorithms to value-based methods and policy-based methods. Value-based methods rely on temporal difference learning. For example, SARSA is a non-policy algorithm that updates its Q values using actions that are actually taken in the next state, while Q-learning is an off-policy method that updates Q value using the maximum estimated value over all possible next actions. Double DQN improves upon standard Q-learning by separating action selection and action evaluation, which helps reduce Q value overestimation. Policy gradient methods takes a different approach. Instead of learning a value function and deriving a policy from it, they directly optimize the policy itself. The policy gradient theorem provides the theoretical basis for this approach by expressing the gradient of the unexpected return in terms of the log probability of actions. The reinforced algorithm is the simplest example of this idea, but it suffers from very high variance because it relies on the Monte Carlo returns. To address this issue, actor-critic methods introduce a value function as a baseline, which significantly reduces variance. A2C further improves stability by using multi-step returns. DDPG extends the actor-critic framework to continuous action spaces using deterministic policy. But in practice, it is often sensitive to hyperparameters and unstable when combined with high-dimensional visual inputs. Among these methods, proximal policy optimization, or PPO, plays a central role in our work. PPO improves training stability by explicitly limiting how much the policy is allowed to change at each update. It does this through a clipping mechanism on the policy update objective, which prevents overly large updates. In addition, PPO uses generalized advantage estimation to balance bias and variance, and it performs multiple training epochs on the same batch of collected data, which improves sample efficiency. These properties make PPO particularly. Next, I'll briefly introduce the shared network architecture used in our implementation. With the exception of the final SOLTA model, all algorithms share a common set of network components. For visual perception, we use a convolutional encoder based on the classic nature CNN architecture proposed by DeepMind. This architecture has been extensively validated in prior reinforcement learning work and provides a strong baseline for image-based control. Most of our algorithms operate on 84 × 84 input images, while the final PPO-based auto model used 96 by 96 inputs due to time constraints. Although this leads to different feature vector dimensions, the overall network structure remains the same. The convolutional encoder consists of 3 convolutional layers that progressively extract coarse track structure, mid-level curvature information, and fine-grained texture details. The output of this encoder is then fed into either a Q-network or value-based methods, or an actor-critic network for policy gradient methods. To ensure stable training in deep networks, we apply orthogonal initialization to all convolutional and fully connected layers. This initialization strategy helps maintain stable activation variance across layers, and is especially important for reinforcement learning, where unstable gradients can easily derail training. Here, I want to briefly explain the core code structure of our actor-critic implementation, focusing on the design data rather than line-by-line details. As shown in the code, the actor and critic share the same convolutional neural network as a backbone. The shared CNN is responsible for extracting visual features from the stacked image observations. After feature extraction, the network splits into 2 independent branches, one for the critic, which outputs a scalar state value estimate, and one for the actor, which outputs the parameters of the policy. In practice, this means that feature extraction is computed only once, while decision-making and value estimation remain independent. This shared backbone design provides 2 major benefits. First, it improves computational efficiency, since the most expensive parts of the network, the CNN, is not duplicated. Second, it ensures feature alignment, meaning that the actor and the critic base their decision on exactly the same visual representation of the environment, avoiding inconsistencies in perception. In the actor head, the network outputs the mean of a Gaussian action distribution, together with a learnable log standard deviation. A key design choice here is that the action mean is produced without any tan or sigmoid activation function. In earlier versions, bounded activations were used to constrain actions, but this introduced a serious optimization issue. In the SOTA version, we deliberately allowed the network to output unbounded raw values and apply clipping only at the environment interface during action execution. The motivation is that bounded activations such as sigmoid or tanh suffer from vanishing gradients near their boundaries. When the agent needs to apply full throttle or extreme steering, actions that correspond to boundary values, the gradients become extremely small, making learning slow or even impossible. By removing these activations, gradients can flow smoothly across the entire numerical range, allowing the policy to learn extreme but necessary behaviors such as full throttle or aggressive steering much more efficiently. This change significantly improved convergence speed and the final performance in practice. Before running large-scale experiments, we constructed a qualitative prediction framework based on the mathematical properties of different algorithms and the dynamic characteristics of the car racing environment. The goal here was not to guess exact scores, but to understand why certain methods should perform better than others. The first score dimension is continuous versus discrete action spaces. Our prediction was that algorithms operating in continuous action spaces would significantly outperform those using discrete actions. The reason is that car control is fundamentally a continuous dynamics problem. Discrete methods such as DQN must quantize steering into course actions like left, right, or straight, which inevitably produces jagged trajectories. This makes it difficult to maintain the fine-grained torque balance required for high-speed cornering. In contrast, policy gradient methods output continuous control signals, typically as the mean of a Gaussian distribution, which naturally leads to smooth steering and acceleration. The second core dimension is on-policy versus off-policy learning. We predicted that on-policy algorithms such as PPO and A2C would be more stable than off-policy methods like DQN and DDPG, although potentially less sample efficient, that is. So car racing involves high-dimensional visual input in complex state transitions. While off-policy methods benefits from replay buffers, they are highly sensitive to distribution shift and Q-value overestimation. PPO, through its clipping mechanism, explicitly limits the size of policy updates, providing a strong form of practical stability. From an engineering perspective, this clipping mechanism offers a very valuable form of monotonic improvement guarantee. Based on these considerations, we divided the expected algorithm performance into 4 tiers. At the top tier, T0, we placed PPO. We expected PPO to achieve scores above 850 and potentially reach soda-level performance. The key reason is that PPO strikes a balance between stability and efficiency. Its important sampling combined with clipping effectively prevents policy collapse under high-dimensional visual input, making it particularly suitable for long-horizon racing tasks. In the second tier, T1, we placed A2C and DDPG. For A2C, we expected stable convergence due to its low variance gradient estimates, but weaker final performance compared to PPO because it lacks a strict constraint on policy updates. This often leads to conservative strategies such as safe but slow driving. For DDPG, although its theoretical upper bound is high as a continuous control method, we expected instability in practice. The critic network in DDPG is prone to Q-value overestimation in high-dimensional visual settings, which typically manifests as strong oscillations in the training curve. In the third tier, Tier 2, we placed double DQN and standard DQN. We expected moderate performance in the range of 400 to 600 points. Beyond the inherent limitation of discrete action spaces, the combination of CNN processing latency and delayed Q-learning updates often leads to bang-bang control behaviors, where the agent oscillates left and right rather than following a smooth trajectory. While double DQN mitigates Q-value overestimation, it cannot recover the precision loss through action quantization. Finally, in the lowest tier T3, we place Reinforce and Sarsa. Reinforce relies on Monte Carlo updates and must wait until the end of the episode to update this policy. In long-horizon tasks like car racing, this results in extremely high gradient variance and makes convergence very difficult. Sarsa, although theoretically stable as a non-policy method, updates based only on executed actions and exports very conservatively. As a result, it easily becomes trapped in simple local optima, such as spinning in place or continuously pressing the throttle without meaningful control. In this section, I'll focus on how we systematically optimize the PPO to achieve stable and high-performance driving behavior, rather than simply relying on the vanilla algorithm. When we first trained PPO using a standard reward function, we observed several clearly non-ideal behaviors. The agent often exhibited suicidal driving, excessive wobbling on straight segments, or spinning in space near the track center. Although the cumulative reward increased to some extent, the learned behavior was far from smooth or robust. This indicates that while PPO was learning something meaningful, the default reward signal was insufficient to guide fine-grained control. And to address this, we introduced reward shaping as the first major optimization. Instead of relying solely on sparse, progress-based rewards, we incorporated dense geometric feedback derived from the car's motion relative to the track. Specifically, we rewarded effective forward progress along track direction, encouraged the vehicle to stay near the center line using a smooth potential function, penalized high-frequency lateral oscillations, and discouraged contradictory pedal usage, such as pressing gas and brakes simultaneously. The goal of these terms was not to hard-code driving rules, but to provide smoother gradients that align the optimization objective with physically reasonable driving behavior. So the second major optimization targeted training efficiency rather than reward design. We adopted several engineering-level accelerations, including synchronous vectorized environments, frame skipping, and decoupling action inference from environment stepping. Together, these changes significantly increase the effective data throughput, allowing PPO to see more diverse trajectories within the same wall clock time. In addition, we enabled mixed precision training using AMP, which further improved frames per second without introducing numerical instability. These optimizations were critical in making long-horizontal PPO training, making it feasible under limited computational resources. However, even with improved rewards and faster training, we observed that the raw action outputs from policy network could still lead to jittery control at execution time. This motivated our third optimization, which operates at the execution layer rather than the learning layer. So we adopted a low-frequency decision and high-frequency execution architecture. Concretely, the policy network outputs actions at a relatively low frequency, while a PID controller operates it at a higher frequency to smooth steering and throttle signals before they are applied to the environment. This design has two key advantages. So first, it separates high-level decision, making them control smoother from the lower level, which mirrors classical control system design. And second, it effectively suppresses high-frequency oscillations that are difficult for a neural network to eliminate purely through learning. And as a result, the agent produces much smoother trajectories, avoids unstable steering corrections, and maintains higher average speeds without sacrificing stability. Taken together, these optimizations form a coherent pipeline rather than isolated tricks. Reward shaping provides informative gradients, training acceleration improves sample efficiency, and execution level smoothly stabilize control behavior. It is the combination of these three layers, objective design, training efficiency, and action execution, that ultimately enables PPO to achieve robust, high-performance driving behavior in the car racing environment. In this section, I'll summarize how we evaluated our models and what conclusions we can draw from the experimental results. For evaluation, we use the average episodic reward as the primary performance metric, which is the standard measure in the car racing environment. Each model was evaluated over multiple episodes after training, and we focused not only on the final score, but also on the training stability, convergence speed, and the qualitative behavior of the learned policy. This combination of quantitative and qualitative evaluation was important because a high reward alone does not necessarily imply stable or realistic driving behavior. Overall, the experimental result closely matched our theoretical predictions from the previous section. Among all tested algorithms, PPO consistently achieved the best performance, both in the term of final score and behavioral quality. With the full set of optimization applied, PPO was able to reach high and stable rewards, while maintaining smooth trajectories, effective cornering, and minimal oscillation. Most importantly, the training process itself was stable, with no signs of policy collapse or severe reward oscillations. This confirms that PPO, when combined with proper reward shaping and engineering optimizations, is particularly well-suited for long-horizon, vision-based continuous control tasks. So A2C and DDPG form the second performance tier. A2C show relatively stable convergence and reasonable final scores, but its performance plateaued earlier than PPO. Qualitatively, the agent often adopted conservative strategies, prioritizing safety over speed, which limited its final reward. DDPG, on the other hand, occasionally achieved high rewards, but its training process was highly unstable. Large oscillations in the reward curve were common, and small changes in hyperparameters could lead to drastically different outcomes. These observations are consistent with our expectation that DDPG has a higher theoretical upper bound, but it's difficult to stabilize in high-dimensional visual environments. So value-based methods, including DQN and double DQN, achieve moderate performance. While double DQN improves stability compared to standard DQN, both methods were fundamentally limited by their discrete action spaces. The learned driving behavior often exhibited sharp steering changes and bang-bang control, resulting in inefficient trajectories and difficulty maintaining high speed through corners. These limitations persisted even with extended training, indicating that the performance bottleneck lies in action representation rather than training duration. So finally, Reinforce and SARSA performed the worst among all tested methods. Reinforce suffered from extremely high variance and slow convergence, and in most runs failed to learn meaningful driving behavior within the training budget. SARSA, although stable in principle, explored very conservatively and frequently became trapped in simple local optima, such as spinning in space or driving slowly without effective progress. These results further highlights the challenges of applying simple or purely value-based methods to long horizon, vision-based control tasks. So in summary, the evaluation results validate both our theoretical analysis and our engineering choices. The clear performance gap between PPO and other algorithms demonstrates the importance of continuous action spaces on policy stability and carefully designed optimization strategies. More broadly, these results show that achieving strong performance in complex reinforcement learning tasks is not solely about selecting the right algorithm, but about integrating theoretical insight with practical system-level design. In this section, I'll present and discuss the experimental results of the baseline algorithms. It is important to note that all baseline experiments use the same basic reward shaping strategy to accelerate convergence. So the differences we observe mainly reflect the intrinsic properties of the algorithms themselves rather than differences in reward design. We conducted comparative experiments on double DQN, NSTIP-SARSA, A2C, DDPG, Reinforce, and a baseline version of PPO. Overall, the results show clear performance stratification, which aligns well with our theoretic predictions. So started with double DQN. Its performance was better than expected, although it operates in a discrete action space. Its training curve showed a slow but steady upward trend. Over this whole course of training, the average reward gradually increased and reached around the mid-600 range. This indicates that under reward shaping, double DQN is capable of continuously improving its policy. The key strength here lies in its off-policy nature and relatively stable value estimation using a target network, which allows it to make efficient use of collected samples despite the limitations of action discretion. So NSTIP-SARSA showed a very different behavior. While its performance improved in the later stages of training, its early stage exploration efficiency was extremely low. The moving average reward started from strongly negative values and only began to improve after a large number of episodes. Although it eventually reached the mid-400 range in the best episodes, the overall average performance remained low due to many catastrophic failures early in training. This reflects the conservative nature of on-policy temporal difference learning, where updates are restricted to actually executed actions. As a result, exploration is inefficient, and value estimates exhibits noticeable instability, especially in the later stages. So A2C, it converges extremely quick, but also stagnated very early. So within a short time, the reward rose to around 300 points and then remained almost unchanged for the rest of the training. Qualitatively, the agent learned a safe but conservative driving strategy, prioritizing stability over speed. While A2C demonstrated better stability than Reinforce and faster convergence than value-based methods, it lacked a mechanism to safely escape local optima. Without PPO's trust region style constraint, it was difficult for A2C to push beyond this performance ceiling. DDPG exhibited a classic failure pattern under high-dimensional visual input. Early in training, it appears to learn a simple strategy, often aggressively pressing the throttle, which led to a rapid increase in reward. However, this improvement quickly plateaued, and the training curve oscillated around roughly 300 points for a long time. The credit network frequently suffered from instability, and the actor became trapped in the local optimum. This behavior highlights a key weakness of DDPG. Although it has a high theoretical upper bound for continuous control, it's extremely sensitive to hyperparameters and difficult to stabilize when combined with convolutional visual encoders. Reinforcement, however, performed the worst among all tested algorithms, Its reward curve exhibited severe oscillations, fluctuating widely between low and moderate scores with no clear convergence trend. Even with reward shaping, the Monte Carlo nature of reinforce resulted in extremely high variance, especially in a long horizon task like car racing. Qualitatively, vehicle control was highly unstable, confirming our theoretical expectations that pure policy grading methods without variance reduction struggle in complex sequential decision problems. Finally, baseline PPO demonstrated the most stable learning behavior among all algorithms. It converged quickly to 400 to 500 reward range and maintained a smooth training curve with relatively small variance. However, it also entered a long plateau and failed to break through to higher scores. Qualitatively, the agent could complete the track, but exhibited noticeable snake-like oscillations and control jitter. The limitation is largely due to the baseline setting, including limited training time, simple reward shaping, and execution at the default physics frequency. Nevertheless, even in this baseline form, PPO outperformed other methods in terms of robustness and training stability, highlighting the practical value of trust region style optimization. Several key conclusions can be drawn from these baseline results. So first, reward shaping alone is not a panacea. Although all algorithm benefits from the shaping rewards, unstable methods such as DDPG and reinforce still fail to learn effective policies. This demonstrates that intrinsic algorithm stability mechanisms, such as PPO stipping or double DQN's target network, are fundamental to performance. Second, double DQN showed surprising potential. Despite the disadvantages of action discretization, it demonstrated stronger robustness and more consistent improvement than DDPG, likely due to more stable value estimation and better resistance to noise. Finally, baseline PPO clearly illustrates both robustness and limitation. Its stable convergence confirms the strength of PPO as an algorithm, but the gap between baseline PPO and the final SOTA version highlights that the algorithm choice alone is not sufficient. Advanced reward shaping, careful hyperparameter tuning, higher control frequency, and execution level optimizations are all necessary to fully unlock the algorithm's potential. In this section, I'll focus exclusively on the training results of PPO model with our SOTA reward shaping design on the car racing V3 environment. So before discussing the results themselves, I want to make an important clarification about score definition. The highest score reported for the SOTA model, around 5,700 points, is obtained under our custom-shaped reward function. This reward includes additional components such as effective progress rewards and centerline maintenance rewards. As a result, this score is not directly comparable to the standard scores reported on the Gym leaderboard, where typical PPO scores are around 900 to 1,000. In this project, the term SOTA refers to the best performance achieved within our own experimental system, or what we call state of our attempts, rather than global state of art performance. For reference, we treat standard PPO performance under the default reward as the baseline, while the 5,700 point result represents the upper performance limit achieved under our specific engineering optimizations. Our primary evaluation metrics is episodic return, since the objective of the task is to maximize cumulative reward over an episode. In addition, we analyze moving average curves, return distributions, stable plateau intervals, and training loss behavior to determine whether training has converged, whether it's stable, and whether any performance degradation occurs over time. From the training return curve, we observe a clear overall upward trend as training progresses. In the later stage, the returns enter a high return plateau, indicating that the policy has reached a stable performance regime. While the raw per episode return exhibits large variance, which appears as strong up and down fluctuations, the 50 episode moving average shows a smooth and consistent increase. So in the final training stage, this moving average stabilizes roughly in the 4,300 to 4,800 range. The best single episode during training reaches approximately 6,100 to 6,300 points. So looking at the return distribution over the entire training process, the overall mean is around 29,090. This value is significantly lower than this late stage plateau level because it includes many low return episodes from the early exploration and non-converged phases. The distribution spans a wide range, reflecting substantial episode-to-episode variation. However, when this distribution is interpreted together with the moving average curve and the learning progress curve, it becomes clear that the later stage performance remains consistently high, with no evidence of long-term regression or collapse. The learning progress plot, which tracks recent window average return over training steps, also shows a monotonic increase followed by a stable plateau, further supporting the conclusion that training has converged in a stable manner. Regarding training losses, the policy loss remains relatively small in magnitude and fluctuates within a controlled range, while the value loss exhibits larger absolute values and noticeable spikes, especially in the middle and later stages of training. This behavior is not unusual in continuous control tasks with reward shaping. Reward shaping effectively rescale returns and introduces additional non-stationarity in the target values that the critic must fit, which naturally introduces the magnitude and variability of value loss. The more important criterion is whether these loss fluctuates coincide with return collapse or irreversible performance degradation. In our experiments, the return curve remains stable within the high return interval despite loss oscillations. Combined with PPO's clipping mechanism, which explicitly limits the magnitude of policy updates, this indicates that the training process remains controllably stable from an engineering perspective. So when we relate these results back to our model design, the performance improvement can be attributed to two core factors. The first is reward structure alignment. By shifting part of the training objective away from sparse title-based progress towards effective forward motion along the track direction and the trajectory level constraints, we provide dense, directionally consistent learning signals. Effective progress reward encourage velocity components aligned with the track tangent, while centerline rewards impose a smooth Gaussian constraint that reduces deviation and off-track risk. The second factor is control level regularization. Penalties on high-frequency steering changes reduce trajectory jitter, and penalties on throttle brake conflict reduce inconsistent action combinations. And together, these mechanisms suppress action noise, improve policy interpredictability, and significantly increase the density and consistency of the learning signal. As a result, PPO can enter a stable convergence regimen more easily and reach a high-performance ceiling within a limited training budget. So finally, it is important to emphasize the scope of these results. This section reports results for a single algorithm, PPO, under a specific sort of reward shaping design. These results alone do not justify a general conclusion that PPO is universally superior to other algorithms. A fair cross-algorithm comparison will require evaluating all methods under the same training budget and evaluation criteria. And with PPO itself, there remains room for further improvement. Future work could focus on systematic ablation and calibration of reward-shaping components to avoid excessive critic fitting pressure, finer-grained hyperparameter tuning, or stage scheduling of PPO parameters, and stricter reproducibility experiments with multiple random seeds and mean variance reporting to strengthen statistical credibility. So in this final section, I will summarize why PPO was selected, what ultimately made the system successful, how the performance evolved from baseline to SOTA, and what the main contributions and limitations of this project are. So the decision to choose PPO as the core algorithm was based on both theoretical analysis and experimental validation. From a theoretical perspective, PPO provides several key advantages that are particularly important for the car racing task. Its clipping mechanism explicitly limits the magnitude of policy updates, which significantly improves the training stability and prevents policy collapse in the long horizon tasks. PPO also supports multi-epoch training on the same batch of data, allowing more efficient use of the collected samples and faster convergence. In addition, generalized advantage estimation reduces gradient variance while maintaining a good balance between bias and variance, which is critical for stable learning under high-dimensional visual input. From an implementation perspective, PPO integrates naturally with a shared actor-critic architecture. The shared backbone improves parameter efficiency and ensures consistent feature representation between the policy and the value network. Using a single optimizer to jointly update the actor and critic allows gradients to fuse in shared layers, enabling collaborative learning rather than competing updates. Together with advantage normalization, gradient clipping, and the clipping mechanism itself, PPO demonstrates long robustness throughout training. These properties make PPO the most suitable choice among all tested algorithms for this task. When compared with other algorithms, PPO shows a clear overall advantage. Reinforce is conceptually simple but suffers from extremely high variance and low efficiency. A2C improves upon reinforce, but without a clipping mechanism, it may still become unstable or stagnate. DDPG is off-policy and theoretically efficient, but in practice requires careful tuning and is prone to instability under visual input. Double DQN and step SARSA are relatively stable, but the reliance on discrete action spaces fundamentally limits their suitability for continuous control tasks. PPO achieves the best balance between stability, efficiency, and suitability for continuous control, making it the most reliable choice in this project. One of the most important factors behind the PPO success in the dual network design with a shared feature extractor and a single optimizer. By sharing the CNN backbone, the actor and critic operate on exactly the same visual representation, avoiding inconsistencies in perception. Joint optimization allows gradients from both objectives to influence shared layers, promoting cooperative learning. Combined with PPO's clipping mechanism, this design ensures stable and efficient training, even under limited sample budgets. Another key factor lies in environment-level optimization. Reward shaping provides dense, geometry-aware feedback that makes learning tractable in a complex. Several targeted. One of the most important factors behind the PPO success in the dual network conceptually simple but suffers from extremely high variance and low efficiency. A2C improves upon reinforce, but without a clipping mechanism, it may still budgets. Another key factor lies in environment-level optimization. Reward shaping provides dense, geometry-aware feedback that makes learning tractable in a complex environment. PID smoothing reduces execution-level action jitter and stabilizes trajectories. The upgrade to 120 HC control further enables fine-grained corrections and smoother execution. Together, reward shaping, PID smoothing, and high-frequency control form a coherent optimization chain that significantly improves both performance and stability. Several targeted network-level improvements also played a crucial role. Removing bounded output activations avoids gradient vanishing near action limits and maintains effective gradient flow. Orthogonal initialization stabilizes activation variance and improves convergence behavior. Gas bias initialization ensures early explorations by encouraging throttle usage from the beginning, effectively avoiding the stationary agent problem. While each of these techniques is simple in isolation, together they substantially improve learning efficiency and robustness. Several targeted network-level improvements also played a crucial role. Removing bounded output activations avoids gradient vanishing near action limits and maintains effective gradient flow. Orthogonal initialization stabilizes activation variance and improves convergence behavior. Gas bias initialization ensures early explorations by encouraging throttle usage from the beginning, effectively avoiding the stationary agent problem. While each of these techniques is simple in isolation, together they substantially improve learning efficiency and robustness. The system evolved through a clear and systematic path. Starting from the baseline PPO implementation, we progressively introduced advanced reward shaping, execution layer PID smoothing, 120 HC control, and finally network architecture improvements, resulting in the final SOTA PPO system. The most important improvement came from reward shaping, which transformed sparse feedback into dense, directionally consistent learning signals. PID smoothing converted raw policy outputs into smooth, executable actions. The 120HC control upgrade enables finer corrections and reduced error accumulation. Network improvements removed optimization bottlenecks caused by bounded outputs and poor initialization. Empirically, baseline PP output yielded around 500 points. After introducing advanced reward shaping and extended training, the system achieved scores above 5,000, but with noticeable jitter. After adding PID smoothing and high-frequency control, the final system reached approximately 5,740 points with smooth and stable driving. This shows that reward shaping is the primary source of score improvement, while PID smoothing is the key contributor to qualitative behavioral improvement. Overall, average return improved from roughly 1,200 to around 5,740, mainly due to the sawdust training strategy. Driving behavior evolved from unstable, snake-like motion to smooth and controlled trajectories, largely due to the PID controller. From an engineering perspective, this validates the effectiveness of a hybrid architecture that combines a rough but powerful learned policy with a fine and reliable execution layer. The project verifies that qualitative algorithm analysis can effectively predict experimental outcomes. It demonstrates PPO's strong advantages in continuous control tasks and highlights the importance of execution layer optimization. Most importantly, it established a complete and reproducible improvement path from a baseline implementation to soda-level performance through systematic engineering refinements. Future work can focus on more systematic reward shaping ablation and calibration to reduce critic fitting pressure. PPO hyperparameters can be further optimized through fine-grained or staged tune strategies. Reproducibility can be improved through multi-seed experiment and mean variance reporting. The approach can also be extended to other continuous control environments to validate generality. Finally, strict ablation studies should be conducted to quantitatively separate the contributions of reward shaping, PID smoothing, and high-frequency control. Despite strong results, several limitations remain. Baseline comparisons were not fully clean due to the early introduction of reward shaping. The SOTA score is not directly comparable to standard leaderboard scores because it depends on a custom reward function. In addition, the final performance gain relies heavily on engineering optimizations such as PID control and high-frequency simulation, which partially mask the limitations of low-frequency policy execution. Ideally, future agents should learn smooth control even under less favorable execution conditions. All implementation code, training scripts, and evaluation tools are provided in the project repository. Demo videos showcase agent behavior across different algorithms and optimization stages, including direct comparisons before and after PID smoothing and under 120 HC control. Together, these resources document the complete process from basic algorithm implementation to SOTA-level system optimization.